Hello again, this is Sample Physics here again, and I'm producing this clip for my Year 10 class studying triple science physics. I've got two diagrams here right now, and if you look at A, now A is showing you an object that's falling through the sky, falling through air. And as you can see from there, that the object is basically accelerating at 10 meters per second squared. What that means is that the gravitational pull is causing the object to increase its speed by 10 meters per second every single second. So in a sense, what that means is that after the first second there will be an increase in 10 meters per second, and after the next second it will increase again by 10 meters per second, and as a result the resultant speed or the velocity is actually increasing. Now, if we now say look at the graph basically on this section here, we can see that as the object is actually falling through the air, okay, there's going to be a uniform acceleration here taking place, and because it's a straight line, and because it's a straight line, it shows you that the gravitational value for obviously gravity is going to be approximately 10 meters per second squared. And you can see that because if we now look at the gradient of this particular line here, marked upwards by between 0 and 2.5 meters per second. So if we now take the gradient of this particular line here, where we got 2.5, i.e. the upward stretch between 0 and 2.5, and across, if you look 0 and 0.25, now if we divide 2.5 by 0.25, yes, we are going to get a value of 10 meters per second squared, which actually closely correlates with what you have here, which is going to be 10 meters per second squared. Now, if we now introduce the same object in a fluid, for example a liquid, now what we're going to be introducing here is an additional force that is going to be the drag force, the resistance force, and this obviously is going to have an effect on the total motion of the object, because when the weight of the object is going to be equal to the drag force, the resultant force therefore is going to be equal to 0, and as a result we can see that the object in a liquid will fall at constant velocity. Now graphically, if we were to show this on a velocity time graph, okay, we can see that yes, we will have some uniform acceleration taking place here, but as you can see that as there's a build-up of a drag force, then what's going to happen is that this uniform stretch here, the uniform acceleration here, is gradually going to change into this pattern here, where we are going to have no further increase in uniform acceleration. However, what is going to happen is that the object is going to reach terminal velocity in a very short period of time. That's purely because there's a resistive force acting upwards, and basically this is the reason why the graph is actually reaching terminal velocity a lot sooner, okay, compared to, let's say for example in air, where this line here, the uniform acceleration here, will have to go a lot further once it actually reaches a constant velocity. So really, if we were to take this example of the object in the air, this will continue to move in a uniform motion, like a uniform acceleration, but eventually, due to the build-up of air resistance, it will actually reach constant velocity as well. It just so happens that if we put an object in a liquid, that obviously the resistive forces are going to cause the object in a liquid to reach terminal velocity a lot sooner. If you have any questions, please obviously post your comments on this on YouTube or on my clip, okay, but we'll see you very soon on the next topic.